With this, I will begin my thesis defense, which I am titling Entangled Landscapes, Neutron Scattering Studies of Magical Magnetic Quantum Crystals Grown in the Spirit of the Atacama Desert. Before I begin the talk proper today, I would like to...
It went a few slides in.
Thank you. This thing is a bit slow. It's a bit of a delay.
Yes.
Might be able to set up the screen share a bit better. Something.
No, I think I think you have the hang of it.
This will work. It's just no, this is it's going to be a little bit annoying, but we'll make do. So to begin this talk, I would like to follow Stanford's official standard procedure and begin with a land acknowledgement. And so I really want to go above and beyond here because, as you will see throughout this talk, this is very important to me. So I invite everyone in the room to close their eyes, take a big breath in while stretching their spine up towards the sky. Take a big exhale out while sighing out all together. One more time. Right. I get more participation in other rooms. What I invite you all to remember as you close your eyes and visualize, the Bay Area used to be a very different place. Stanford University sits on Ohlone land that was never ceded by them. The Ohlone are very wise people. I imagine what their lives might have been like. If you go down to the Bixby Bay shore, you have wetlands with beautiful birds and waterfowl that remind me of the ducks I fell in love with back at home in Minnesota. The entire bay, all the way from San Jose up to San Francisco and beyond, used to be like this. We lost a lot when institutions like Stanford went in. And the Ohlone also paved the way for many modern technologies. The roads we travel on by car were originally trails blazed by them. I pray that in part through this talk and ongoing, repatriation and, knowledge regaining efforts, we can regain some of the knowledge. Nothing else. I think the Ohlone were experts at managing California wildfires, and it's this kind of knowledge that I pray we regain. So, amen, aho, so it may be. With this, I'll begin my talk proper. So I will start my talk, since this is a thesis talk for a general public audience, by talking about the physical origins of magnetism. So the origin of magnetism in matter is actually derived from the level of single particles. Anything big like a hunk of iron that is magnetic in bulk is in fact magnetic because it's made up of a bunch of tiny little magnets at the individual particle level. The most important source of magnetism in atoms is the electron, which contains a relatively large moment of 1 Bohr magneton, just because of the way it is. It's intrinsic, just like its charge. Another way electrons can produce magnetic fields is by more or less orbiting around their host atoms. And if we follow, Faraday's law, we see that moving charge ends up generating a net magnetic field. This magnetic field is also on the order of a Bohr magneton and can be very important in some atoms. One thing that I will allude to that will become important in this talk is technically if this is just a single atom in a vacuum, it's not really having a magnetic field that points in defined direction, much like iron or a bar magnet would, but it's in a quantum superposition of all its possible states. So, and we'll see more kind of consequences of this quantum mechanics throughout this talk. So with this as an introduction, I will now move on to bulk magnetism, and this arises by just some coherent order of individual magnetic atoms. There's two kind of flavors generally how they can do this. They can either align anti-ferromagnetically, meaning each individual atomic site prefers to anti-align its magnetic moment to minimize energy, or in other cases, it minimizes energy by aligning the magnetic moments. One thing I will note is that I learned in Ian Fisher's quantum materials class that the reason it can do either of these things is it minimizes energy not as a result of the direct magnetic exchange between atoms. If this were the case, everything would be a ferromagnet, but because the wave function of the electrons can make the electrons further or apart or closer together on average, depending on how they flip their spins. So this actually does this to minimize electric energy, even though it's an emergent magnetic effect. The final and most important kind of magnetism that will be pertinent to this talk is the animation's a little choppy, but the spin liquid. So as it turns out, if you heat up any material enough, eventually its magnetic spins will start to liquitize before the chemical lattice becomes unstable. And you see that with the rotating magnetic moments here. For iron, I believe this happens around at 400 Fahrenheit, and most things magnetically melt before the physical solid melts into a liquid. So with this, I will now introduce frustrated magnetism, which is a more exotic flavor of antiferromagnetism. And this occurs on more complicated crystal structures where these interactions lead to really cool exotic magnetic order. So the lattice I'll be talking about the most today is the Kagame lattice, which is the super cool mystical 2D lattice that is more or less made of this tessellating pattern of star data that infinitely fills two-dimensional space. We zoom in on any one atomic site, we will see that it has, it's part of two triangles with three neighbors. So if you try and actually pattern this antiferromagnetically, if these are magnetic moments sitting on these sites, you'll see that they can't point 180 degrees to each other. The best that they can do is this kind of 120-degree order. The problem with this is that there's actually infinitely many ways these 100-degree or 20-degree orders can tile over the Kagame lattice. So this causes what we call a ground state degeneracy. In materials that are Kagame lattice that actually order, what happens is there's some higher order term, like say a ferromagnetic second neighbor interaction that allows this frustration to be alleviated and potentially can lead to these ground states ordering at very low temperatures. So this sets up the stage for what I like to call magical magnetism, or my advisor Young prefers exotic magnetism. Same thing in my view. So if we take the most exotic 2D lattice, arguably the Kagame, and put the tiniest possible quantum spin on it, the spin 1/2, the magnetism becomes so frustrated that it can't actually find a ground state, even all the way at absolute 0 Kelvin due to quantum mechanical effects. So this is fairly analogous to other exotic quantum effects, like say superfluid liquid helium, that due to exotic quantum effects, it won't solidify even at base temperature. So we have a lot of competing ground state, and this state of matter is called a quantum spin liquid. There's several different ways to describe this as physicists. The original proposal by Phil Anderson, which occurred all the way back in the 1970s, was that this would be some kind of resonating valence bond crystal. So here I have a related triangular lattice, and I have these blue circles which indicate a singlet. So both of the spins in the singlet are in a quantum mechanical entangled state. So neither of them truly have a well-defined direction, but together they're antiferromagnetic such that they have no net magnetic moment. They're kind of pointing opposed, but they're also kind of not pointing in a real direction. Really fun quantum mechanical stuff. And then Phil Anderson proposed that more or less kind of like how the electrons in benzene resonate around in a ring, we get a resonance between kind of all possible tilings of this valence bond crystal. A more general case of this is a longer range quantum spin liquid, and this is what we're hoping to achieve here, in which this kind of quantum entanglement isn't just confined to nearest neighbor singlet-like sites, but in general, you can kind of have this quantum magnetic soup of atoms, all being kind of in indeterminate states in their wave function, correlating potentially even across very long distances across our lattice. So what is the hallmark signature that would separate a quantum spin liquid from an ordinary magnetic system? So one of the things that we tend to look for in our studies is its magnetic excitation spectrum. So we have a ferromagnetic order system and we impart some energy into it. What we see here is the spins like to wobble relative to each other. This costs some energy. So this state kind of has some non-zero energy and momentum. But it's very well defined. These modes are very sharp because all of these moments are very well defined, pointed relative to each other. They spin on by contrast. What happens is I did the best I could with ChatGPT. This graphic is okay, but not the best. It's more or less you have these, singlet states that can break into two well-defined antiferromagnetic spins in some kind of particulate-like interaction. And then these free spins become spin-ons that can actually propagate independent relative to each other, unlike the magnon. So this is a static image. As hard as I tried to animate this, it would have been cool. But we can see that more or less this unpaired spin can kind of move freely across the triangular lattice, and the other singlets kind of part ways to make way for wherever it's moving. What's interesting and cool about spin-ons, and we'll see later in this talk, is because of their very nature, as I outlined here, they're more free to occupy a more continuous span of momentum modes. just because of how they propagate. And I think I've kind of demonstrated a little bit of that here. Oh, yeah, one more note. It's going to come up later. One thing about most magnons, some higher order interactions can alleviate this, is they tend to be what's called gapless, at least in the simplest models, meaning that the lowest energy magnon has essentially zero energy. You can perturb these things continuously with very small energies. There's some predictions for quantum spin liquid states that there's some minimum energy you need to impart on this lattice to actually have it absorb a magnetic mode. So that's a key question that we will return to very shortly in this talk, because it's very entangled with the quantum spin liquid problem. So with this, I have some potential applications of magnetical magnetism. You're like, all right, Aaron, why do we care about this exotic quantum magnetic soup? So one of the coolest applications to me is that it could be used to store much more dense information. So the way classical computers store information is pretty cool. It just consists of a bunch of magnetic bits. Literally, like if you have a platter-like hard drive, it consists of a bunch of really, really tiny ferromagnets that either point up or down. One of them represents a 1, one of the other 0. You have some Faraday read-write head, which is just like a current loop where a current gets induced as this platter spins over this loop, and it reads out all the really tiny ferromagnetic states. And it's a kind of amazing how small we've made this magnets and how scalable this technology is. Because like this display, for instance, is 4K. So it's like 4,000 by 2,000 pixels. Each individual pixel has like 3 256-bit numbers to represent the color. So you can imagine how many individual tiny little magnets we actually need to represent this screen. It's kind of insane. So what we've done as humans, because we try and always make things more informationally dense, make our computers bigger, make our large language models better, is we've made our magnets so small that now if we make them any smaller, they become quantum objects, so we can't make our hard drives more dense. What is the solution to this? To embrace the quantum nature of our magnets and instead store information in qubits. So qubits are great in that they're potentially exponentially more information dense than regular bits. The reason for this is generally if you have two qubits that are entangled with each other, they occupy, both of them occupy the 0 and 1 state at the same time, meaning that for n qubits, they can represent 2 to the n classical bits of information in their entangled wave function. Here's the example with 2 qubits representing 4 unique states. With 3, it would be 8, 4, 16, so on and so forth. So this is an amazing technology that could continue Moore's law and continue to make our computing exponentially better. However, it's really hard to experimentally realize. The main problem for this is that it's really hard to actually enforce long-range quantum coherence. It's a really rare and fragile thing. The beauty of our system is that if it is in fact a quantum spin liquid, it kind of already has this long-range entanglement potentially baked into the system. So there are at least some proposed devices that we could go about engineering maybe someday in the future, where we pattern some kind of semiconductor device on the top of our spin liquid in a way that it couples to its topological, quantum spin liquid modes in a way that we might be able to read and write out a stable qubit. Especially if the spin liquid ends up being gap, it would be what's called topologically protected, which would potentially make this quantum memory more stable than other proposals for quantum memory. So this is where this is all going. So with this kind of exciting motivation set up, here's some potential host materials that can actually host exotic magnetism. So we specifically try and grow 2D materials with the least amount distorted Kagame lattices possible with the spin 1/2, like I said. So here's the main ingredient of Zn-Barlowite and Herbert-Smithite. You can see this is copper 2+, has the spin 1/2, organizes into 2D sheets of Kagame lattices like this that are nearly undistorted. Furthermore, these crystals, if you look at them, like if I show you, like I have some here today, you think, Aaron, these are 3D crystals. Well, not really, because the magnetism only lives on these 2D layers, and they're separated by what are mostly non-magnetic interlayers, meaning the magnetism is principally 2-dimensional. With that, though, there is a bit of a tiny caveat. So one of the reasons I studied Zn-Barlowite in addition to Herbert-Smithite is that there's some differences between them, and this can kind of help us tease out some remaining questions in the quantum spin liquid field. So the main way that Herbert-Smithite differs from Zn-Barlowite is in its layer-to-layer stacking. Zn-Barlowite's relatively simpler. The Kagame layers line up right on top of each other, whereas in Herbert-Smithite, there's like this kind of 120-degree twist every layer, such that you only get a layer match every 3 layers up or down. this has dramatic effects on its interlayer environment. So again, the caveat is that sometimes this interlayer site gets filled with a magnetic copper ion rather than a zinc ion. Zinc and copper are nearly chemical identical, so they can kind of do that. And it's frustrating because this could potentially ruin our quantum spin liquid state, lead to some interlayer coupling. So there's been some questions about it. But since these layer-to-layer stackings are different, this impurity environment is very different between these materials. So in zinc barlowite, when this impurity occurs, it will ferromagnetically couple to one of the Kagame layer sites, creating a slight Jahn-Teller distortion. Whereas since the layers are twisted in Herbert-Smithite, it can't distort towards one of the lattice sites because it wouldn't know which site to distort to. And the couplings actually, I believe, are anti-ferromagnetic rather than ferromagnetic in zinc barlowite due to its different coordination environment. So both potential Kagame quantum spin liquids, but different in our impurities, which is why we study zinc barlowite, because impurities are really the main lingering question for those who doubt that these materials are quantum spin liquids. So with this, I will start with related experiments on the slightly less exotic, but very cool Barlowite II system that also helps us tease out individual details of our more exotic zinc Barlowite system. So again, for mom and dad in the audience, since the general public is here, I will give a brief introduction to neutron scattering. And it's really cool. Neutrons are but the world's tiniest little magnets, and they don't have any charge, so they interact only with our nuclear and magnetic lattice. So we more or less use it as X-ray diffraction, but like determining magnetic structures instead of pole structures. So I'm like a little magnetic Marie Curie is how I like to think of myself. So this is how we learn about our magnetic structures. My predecessor, Rebecca Smaha, did a lot of this also with X-rays. You can study magnetism. It's a little less trivial than the subject of this talk. But we find barlowite even in of itself, which differs from zinc barlowite in that its interlayers are all kind of spin 1/2 copper. It facilitates exotic long-range order at ultra-low temperature. So these ordering temperatures of 10K and 6K are much, much lower than typical magnetic ordered systems, like say something like iron, right? So it kind of points towards the weakness and exotic fragile nature of this material. What's more interesting about barlowite is it actually has two unique magnetic ground states, and we can repeatably manifest these magnetic ground states simply by growing the barlowite from different synthesis pathways. And although this is repeatable, there's actually no noticeable difference between barlowite 1 and 2 in terms of their room temperature structure. So I think this really highlights how fragile, delicate, and cool these magnetic ground states are in these barlowite systems. So I'll start with the slightly less exotic barlowite 1, which manages to find magnetic order for kind of this orthorhombic distortion. This interlayer moment ends up kind of facilitating some long-range magnetic order that primarily has an out-of-plane character beneath 10 Kelvin, with lots of structural distortions accompanying it to kind of break up the perfect Kagame lattice motif that would be nearly perfectly frustrated. Barlowite II is more interesting for us because it is, we think, slightly more like the quantum spin liquid state. It achieves this really exotic pinwheel-like magnetic order on its Kagame lattice that's principally a 2D magnetic order in principle. And it's really cool because this magnetic structure that we fit to it has Q = 0, 0 in plane magnetic moment. You see the moments canceling each other out pretty much in a perfect 120-degree fashion. And like I said before, this is all facilitated by this ferromagnetic coupling between the impurity and its nearest Kagame layer moment. So with this, Barlowite II is even more cool and interesting because it not only has potentially one really exotic magnetic ground state at low temperature, but two, separating it from essentially any other magnetic material that I'm familiar with. So I told you about the base temperature less than 6 Kelvin ground state, but as we look at our neutron scattering data, we see that some peaks start getting affected at 10 Kelvin rather than 6 Kelvin. And although our results are much, much more preliminary on this, one thing that is at least self-consistent with our results on this is that this could be a really exotic thing called a valence bond crystal, kind of like the resonating valence bond thing I showed you earlier, but it's not a liquid state. These singlets kind of remain crystallized into our lattice. And then our expectation is as we cool in temperature, the kind of maybe the mean field or exchange generated by these interlayer spins kinds of energetically ends up breaking up these singlets. So with this as kind of motivation, we want to see what happens to this exotic magnetic structure in an applied magnetic field. I think I've demonstrated that these systems are incredibly sensitive to perturbation. So adding one more on top might manifest a new exotic structure and allow us to learn more about this material. So the way we do this is by elastic neutron scattering at Oak Ridge National Laboratory. And as Young alluded to earlier, these experiments are really hard. I'd like to give a shout out to my collaborator and mentor, Wei He, as he co-aligned, I believe, over 1,000 crystals, right? Over 1,000 Barlowite II crystals to make this experiment possible. If that wasn't magical enough for everyone in the audience, as it is, I'll also mention that Oak Ridge National Laboratory is a huge government facility that I think produces on the order of 10 to the power of 30th neutrons per second that end up going through our sample. And yet, as you will see, we still only get about 1,000 scattering counts per 5 minutes of the kinds of scattering we actually want. So this is very much bleeding edge, cutting edge, barely there science that I think is really cool. So with this, here's some magnetic susceptibility data that we've taken, much simpler measurement to execute, but we see a tiny amount of hysteresis here. And this is already enough to suggest that we're kind of driving the system into a different magnetic phase as we ramp up the magnetic field at base temperature. So with this, here's what my raw data looks like. Kind of like Young was saying, this gets to the point that I was making a bit earlier in that our experiments are terribly hard. Most of our scattering is nuclear. As we can see, we try and fit the magnetic peaks by taking the difference between a temperature just above our magnetic ordering and the base temperature. And any additional difference is presumed to be mostly due to magnetic scattering. And we can see that this difference is incredibly small, especially us, because we're measuring a very frustrated magnetic system with very tiny magnetic moments. This difference is much larger for most scatterers. And as I will come back to at later points in this talk, this essentially means we have to develop new background subtraction methods that aren't field standards. So this was a large part of my work for this thesis. So with all of that being said and done, here's the actual magnetic peaks that we were interested in for this study. And we can see a lot of really cool, clean, powerful results already. One is that some peaks are field enhanced. So this 101 peak at base temperature is basically non-existent, but when we apply a magnetic field, it ends up being non-zero and pretty clean, which is cool. In contrast, the 102 goes from being a very well-defined peak at 0 Tesla to essentially statistically insignificant at 8 Tesla. So these different peaks are telling us about different correlations between Kagame to Kagame layers. And it gives it, and this kind of information gives us a hint about what is correlating or anti-correlating either a layer away in the 101 case or principally 2 layers away in the 102 case. So this gives us a lot of hints about what potential magnetic structures are feasible. The other thing I will mention is that we measured a bit less, but it's still some data in this kind of exotic BBC state. And it was kind of at least self-consistent with our original hypothesis. So in the 100 peak, we noticed that it is field suppressed, but still existent in 8 Tesla. Whereas for these 8 Tesla potential valence bond crystal state, we go from essentially having no peak to a fairly clean peak. So at least my preliminary hypothesis is that we might be destroying our valence bond crystal and maybe driving this intermediate phase towards an ordered phase that might be more similar to our in-field base temperature phase. So with this, here's a summary of all the integrated intensities of all the peaks I measured. Anything with the X on it is statistically insignificant from 0 and should probably be ignored, but I include the fit values just for completeness. And so like I said, the main trends are that our 10 even peaks and 0.501 peaks are suppressed at base temperature, whereas the 101 is enhanced. This is the key ingredient for our magnetic model that gives us the biggest hint. And the other thing I will say, like I kind of alluded to earlier, is that our 8 Kelvin and 2 Kelvin data become qualitatively more similar in this applied magnetic field. So with this, I did some actual quantitative modeling to try to guess what's happening with our Q equals 0 structure when we apply a magnetic field. So unfortunately, this beam time still took a week and I only got 5 data points. So I try my best, but I'm working with 3 3-pitting parameters and 5 data points. So this is hand wavy, but maybe in the right direction. So I apply these 3 different steps, allowing the whole pattern to rotate in plane, allowing these red moments to cant more or less in and out of plane, which was already an ingredient of our 0 field model. And then fitting mean squared error to the peaks, I kind of come up with a magnetic model that looks like this. And here's how the mean squared error fits actually look. As we can see, it fits to the 100, 101, and 0.501 peaks incredibly well, more or less within their error bars. But the 102 and 104 peaks, we were just not fitting well. Try as I might, many models, we just couldn't fit it. One thing I will note is that our original magnetic infield model, isn't necessarily fully determined. It's still up to experimental questions, so I could be starting from the wrong value. But secondly, that model also had trouble capturing the 104 and 102 peaks. So these ended up being our largest nuclear peaks by far. I think, a factor of more like 1,000 bigger than our magnetic peaks rather than a factor of 100. So one possibility is that we're just not accounting for some thermal diffuse scattering or Debye-Waller effect, and maybe these reported values aren't solely due to magnetic peaks. But it's something we'll have to potentially, measure more peaks to look into and further refine our model, because it's a slight inconsistency. The next step then would be to look at this model we fit and see if it's consistent with energetics when we apply the magnetic field. In an ideal case, we'd have kind of the infield structure decrease, its CMON energy as a compromise for maybe a bit increased Heisenberg energy such that its net energy is still lower than the Q=0 state in field. What I will say is things are qualitatively going in the right direction in this model, but about an order of magnitude off. Our Heisenberg energy gets worse by about 2 millielectron volts, and our Zeeman energy gets better by about 0.2 of a millielectron volt. So the next step, I think, would mostly be to find more peaks and fit more peaks to try and get a more realistic model, since we're just so under constraint right now. It's hard to know where even to search. But there's some extra perturbations that I thought of too that might minimally affect how we fit our structure, while hopefully making these energetics make just a little bit more sense. But it seems that we're at least hopefully going in the right direction. So with this, here's the summary. We measured Barlowite II in an applied magnetic field. This magnetic field clearly drives some sort of magnetic phase transition, of which in-plane canting is likely a key ingredient. I'd say our results seem to support that just from the dramatic field growths and disappearances. And like I said earlier, we at least have some qualitative suggestions that our valence bond crystal intermediate state is getting destabilized by this applied magnetic field. Whew, that was a lot, hopefully exciting. And the talk's only going to get more exciting from here, because now we get to talk about the hyper-exotic magnetism, my favorite material in Zn-Barlowite. So with this, I will start with the very start of my PhD and mention that these crystals are incredibly difficult to grow. The primary difference between Zn-Barlowite and Herbert-Smithite that makes its coordination environment differ is that Zn-Barlowite is fluorinated while Herbert-Smithite is chlorinated. Not sure how many of you here have worked with fluorine, but it's really annoying. It likes to eat basically everything, including quartz that we typically tend to grow our crystals in. So we had done some preliminary growths where we put the fluorinated fluid in, eats our test tubes, and the thing explodes, and then you have to clean up hazardous fluorinated liquid all over the lab. It's not good. So what I did is I sealed this fluid in Teflon, which is already fluorinated, so it can't be eaten by fluorine. The problem with that is that we still need to seal the quartz. And quartz, to seal it, you need to melt it at around 2000 degrees Celsius, whereas Teflon, to seal it, you need to melt it at around 400 degrees Celsius. If you do the math on that, it becomes really hard to seal this quartz without melting this Teflon. So the solution I came up with, in addition to a lot of work on getting this Teflon seal to be reliable, is to make a longer plug so we can seal the quartz away from the side of the Teflon. And it's worth mentioning here that quartz in itself is a really kind of incredible and exotic material in its own right. Quartz is such a bad thermal conductor that you can literally be at 2000 degrees Celsius here and less than 400 degrees Celsius here. Kind of a marvel of physics in its own right. But anyways, like Young said, it's not all done after that. After all that ado, we put it in the lab furnace for about 9 months. So I call these crystals my babies, because they take 9 months to grow and a lot of labor goes into them. And unfortunately, a lot of them, oh, I wouldn't say that. A lot of them don't turn out, and we don't find out until about a month in, which is probably. So So with this, when I finally create a good baby, we need to do some baseline measurements to make sure it's going to grow up to be the strong adult of science that we need it to be. And so the first characterization we do to kind of look for quantum spin liquid behavior is we measure its magnetic susceptibility. A key hallmark of a quantum spin liquid is that it has no phase transition and has really exotic susceptibility behavior. So for comparison, most materials with regularly periodic ordered magnetic moments end up freezing, and you can see this in susceptibility as some kind of spike in their ordering temperature due to the phase transition. Zn-Barlowite has none of this. This is already pretty weird, but normally when a material does this, it's something called like a spin glass, in which case you'd notice a splitting in your susceptibility if you cool it with an applied magnetic field or without an applied magnetic field. And we see absolutely no splitting within our error bars. So this strongly suggests that this is not an ordinary spin glass by any stretch of the imagination. The other thing we can do to kind of support with our susceptibility data is do a Curie-Weiss fitting. And this fitting suggests a very negative Curie-Weiss temperature. This is correlated to antiferromagnetic exchange in plane. So this suggests that our antiferromagnetic exchange in our plane is very strong in these materials, which would also beef up its potential to be a QSL state. And I'll also mention its theoretical frustration parameter is infinite because at least down to like a couple of microkelvin, we note that it doesn't have any ordering temperature. So these are basic characterizations. We've showed everyone this.
Microkelvin? Microkelvin?
Yeah, I believe 100 microkelvin is the lowest we went. No, millikelvin. Sorry, Ian, thank you. Yeah, a bit different, but who knows? If we got to microkelvin, I don't think we'd find ordering anyhow, but who knows? Someday. Anyways, so to measure these crystals, we start with zero field inelastic neutron scattering. And we do this at Oak Ridge National Lab at my favorite beamline end station, one of the coolest, most modern advanced scientific instruments in the world. That is the cold neutron chopper spectrometer, which is literally just like neutron bowling. So the way inelastic neutron scattering works is you take a packet of neutrons, you shoot it at some certain speed at our bowling pins, our crystals. So it goes excites some magnetic interaction in our crystals, hopefully. And then when the neutrons do that, much like a bowling ball hitting pins, the neutrons will leave with slightly less energy and a different momentum they came in with. And the magnetic mode in our crystal will have, the reciprocal energy mode and momentum mode excited when we do this. So this is all amazing to me. We have such a good grip on clocks as physicists that this all happens within like, I think a couple of microseconds, and we can still see the neutrons losing time due to their interaction with our crystals in which they lose energy. So this is how we get inelastic scattering data to measure our magnetic excitations directly by probing it with. Uh-oh, someone's saying something.
Yeah, can we mute everybody here?
It's Rush. I can mute him. Okay, I think that worked. Okay. Rush, please mute. Okay, thank you. So when we do this, like I said, kind of a recurring theme of this thesis is we measure the weakest possible magnetic scattering. So we always end up running into weird, exotic, interesting backgrounds that no one else really has to contend with. So the background that we found was this chiral-like feature, which was a mystery for several months in the Lie group. We knew it couldn't be real because if I showed you on the previous slide, we co-aligned over 180 crystals. If there was some chiral feature in our magnetism, it would have to show up in both handednesses because presumably about half our crystals are upside down relative to each other. So I did probably the proudest work in physics of my thesis in that I fully characterized and proved that these chiral-like features were a result of elastic Bragg scattering bleeding into our inelastic data. And this allowed us to think about what kind of background subtractions could actually deal with it. The saving grace is that at phase temperature, the crystal has no energy itself, therefore it cannot impart energies to neutrons, making them speed up and arrive at the detectors earlier. However, because the neutrons are Gaussianly distributed, some neutrons end up elastically scattering and falsely showing up with higher energy. Anyway, so that's what we use to subtract the Bragg peaks, is more or less this data set is the magic, because we can prove with 100% certainty that it is just Bragg peak background. So we do some tricks and detailed balance that was outlined in Helton for a different instrument and adapted to this instrument in our studies, and we finally, voila, get more or less 100% background free data. We're not quite done yet because, like I said, even though I counted for 15 hours and had the full support of the US government and the Department of Energy behind me for a week, our statistics still really suck because this experiment is really hard. Thankfully, our crystals are 6-fold rotationally and mirror symmetric, and so that allows us to average 12 equivalent points to finally get clean data out of this. So with our clean data, we can finally compare to Herbert-Smithite, and what we found is some incredibly exciting neutron scattering results. So I'll start with the slightly less exciting results and build up to the really big hurrah here. First is that Herbert-Smithite and Zn-Barlowite look very different at low energy. If you recall my earlier slides, the principal difference between Herbert-Smithite and Zn-Barlowite is in their impurity environments. So this would suggest that the scattering must be impurity mediated. Indeed, we have an empirical model of which I will show you the details slightly later, but our empirical model tends to agree that the scattering is impurity dominated, suggesting our low energy scattering is the result of our magnetic interlayer impurities. The more exciting result is that when we go to high energy, Herbert-Smithite and Zn-Barlowite look incredibly similar, which we would expect to be a result of the Kagame layers because that's what they share in common, and indeed our modeling also supports that. Another interesting feature of this data is if we look above possible impurity energies, which are the bright intensity scatterings here, we see that we get a kind of almost dispersionless strong scattering that's kind of barely momentum and energy independent, which is again kind of a hallmark that we wouldn't expect of most magnetic excitations, but are possible for exotic things like spin-ons. So this result provided some really strong evidence that not only Zn-Barlowite is a quantum spin liquid, but probably also that Herbert-Smithite and Zn-Barlowite are quantum spin liquids. So we can do further characterization of this data, of course, to strengthen our argument. And one would be doing temperature statistics. So if you've taught in statistical mechanics, like I have at this university, you'd know that if you have some energetic magnetic modes at one temperature and you know what statistics they obey, you can predict what these energetic magnetic modes, how they might populate themselves at a different temperature. So indeed, we do this from our 1.7K data. We try and extrapolate to our 40K data using traditional statistics of things like magnons or dimers. And we see that this fails horribly, which is actually good. This supports a quantum spin liquid state. Many theoretical proposals of different quantum spin liquids actually propose anyons or some kind of more exotic thermal statistics. And this is at least somewhat self-consistent with that, even if it's a bit more indirect evidence. So now, as I promised, I will go into...
Going back to the last slide, could you just, you said on the right that the attempt to explain things with magnon models doesn't work. Can you just explain what on this plot you're trying to account for with those?
Yeah. So more or less, we have this data set at base temperature around 2 Kelvin, this data set at 40 Kelvin. So for something that's normal, like a magnon that's bosonic, we can apply Bose statistics. And if we have like the energy spectrum of our occupation, we should be able to predict it at the higher temperature just by using the Bose factor, which is what I did. And it failed, so it suggests that this mode doesn't thermally evolve like magnons. Okay, so with this, here's a little bit more refined details about our magnetic model. So one thing that's neat that we can do is we know where all of our magnetic moments live on our Kagame lattice site because we've characterized it quite well with X-ray scattering, among other things. So what we can do is we know the momenta that would be associated roughly with magnetic correlation at this bond length. So we can do a magical Fourier transform, kind of put all of these real space bonds into reciprocal space-like patterns that represent our scattering. We get a bunch of pretty plots that look like this, and we can add linear combinations of them more or less to fit our data. And that's why I could say that we modeled certain things to be Kagame or impurity dominated. Here's some more details on that. The most exciting detail about this is that we see that we're impurity dominated at low energy, and that impurity scattering tends to go away as we increase our energy, which is kind of more or less what you'd expect turn the energy spectrum of like a damped harmonic oscillator of a relatively independent magnetic impurity moment. Meanwhile, our Kagame correlations are strong and only go up with energy. Our largest Kagame correlation being the strong antiferromagnetic nearest neighbor correlation, which is self-consistent with the antiferromagnetic exchange in order that we find in Barlowite II. Another interesting thing I'll say about the Kagame correlations is that both the second and third nearest neighbors were found to be ferromagnetically coupled with each other, and it's actually reasonably difficult to find self-consistent classical orderings in which both of these exchange criteria are met, which kind of points towards maybe that this thing is indeed in more of a magnetic liquid-like soup state like we want, although of course there's so many ways to tile the Kagame lattice, it doesn't necessarily preclude it either. So finally, I will say one of the most exciting results from this initial CNCS run is that we found an energy gap. This is something that many of our collaborators have purported to find with NMR, but the results weren't necessarily considered conclusive. This is a more direct measurement. So like I said, we have impurity scattering that we measure as a damped harmonic oscillator at low energy, but in addition to this, we notice this kind of uptick in scattering at all momentums, but specifically more so at high symmetry Kagame related momentas. And this suggests that there's additional scattering coming from the Kagame layer that kind of turns on at around 1 millielectron volt. There are some theoretical theories of quantum spin liquids that predict the quantum spin liquid is intrinsically gapped, meaning if there were no magnetic impurities, that we'd have no scattering here and it would essentially turn on at around 1 millielectron volt. So I think this direct evidence of a gap, or at least a bump in scattering at 1 millielectron volt, does support the theory that not only that Zn-Barlowite is a quantum spin liquid, but that it could in fact be a Z2 topological quantum spin liquid, as opposed to something like a U1 quantum spin liquid, which would be theoretically predicted to be perfectly gapless. So like I said, that was the crown jewel of my thesis. The CNCS run was always what we were going to be most excited about after I kind of finished growing my groundbreaking crystals. Here's some additional CNCS runs that we did that kind of provide additional information and supporting data. So the first thing I will say is that all the data I showed you before was done at an incident energy of 3 millielectron volts for the neutron. We can measure higher momenta and higher energy excitations if we come in with faster neutrons. Of course, where bowling balls moving faster, we can knock the pins around more, right? So when we do this, we notice that we get this still gorgeous 6-fold hexagonal symmetric pattern. And all of this is somewhat self-consistent with our Kagame scattering being dominant above the 3 millivolt regime too. Unfortunately, these data sets are slightly harder to fit. One reason for this is you can see the presence of phonons come into play because we're now above energies and momentums where we can start physically vibrating the lattice with our neutrons as well. And at really, really high energies, this gets really messy. But I will say that we still kind of see those Kagame-like star arms of magnetic scattering. So to start, we just did the laziest thing, and that's kind of to crop out anything in momentum. That's where phonons occur or aluminum lines or anything else that is messing with this data. We didn't take higher temperature data at these energies too, so we can't do the Helton subtraction that I showed you earlier that helps deal with some of these backgrounds. So these model fits, are fitting to way, way, way less data, but I will say it was at least self-consistent with our low energy trends. We might write a short paper on this sometime soon. So with this, here's a stronger kind of secondary result that came out of additional experiments I performed at Oak Ridge National Laboratory. And this is a more detailed model of the impurity environment of Zn-Barlowite. If you're paying extra close attention and you're a star physics student, you might have realized I glossed over an important detail, and that is that these impurity sites sit at slightly off-center sites relative to the Kagame lattice when they appear. And since it's the impurities that we're concerned of having magnetic correlation and not the zinc, we therefore should be fitting two separate impurity terms to this first nearest impurity to Kagame layer moment, one slightly further away, which would probably be antiferromagnetically correlated, one slightly closer, which should be ferromagnetically correlated, rather than what we did in our first pass in our Nature paper, which was just to model it with one term. So this Jahn-Teller distortion is fairly substantive. It's about a 10% difference in bond length. And this is kind of a neatness of Fourier transforms. You can see the slightly shorter ferromagnetic bond when we get it through the Fourier funhouse ends up slightly dilating more or less the same pattern. There's a slightly longer antiferromagnetic bond ends up shrinking the pattern. The problem with this and why we didn't immediately do this in our Nature paper is these two models are only about 10% difference from each other in terms of their dilations, which means they can kind of substitute for each other very well as fitting parameters from a fitting perspective. So it's very hard to disambiguate them. One thing we can do to help disambiguate, especially since these impurities have an out-of-plane character to them, is to add out-of-plane scattering. And we can see in the HOL zone that these patterns have a bit of an additional difference that helps disambiguate our fits. One final thing I'll say with respect to out-of-plane data is that it also allows us to check for potential Kagame layer to neighboring Kagame layer correlations, which of course is just non-existent when we're measuring in plane, or we're not sensitive to rather. So here's some simultaneous fits that I did to both of our HKO data and out-of-plane HOL data, and the results were really exciting. I got that the ferromagnetic coupling was indeed fit to be ferromagnetic, and that the anti-ferromagnetic slightly longer impurity bond was indeed found to be anti-ferromagnetic. So this suggests that our neutron data, after all that processing, is high quality enough to disambiguate this impurity site. What's even more exciting about this is if we take the difference between the ferromagnetic term and the anti-ferromagnetic term in terms of their magnitudes, we get the fitted ferromagnetic value of our averaged IKN1 term from our averaged fit that we presented in our Nature paper. So to me, this strongly suggests that we're doing a really good job of capturing the unique impurity environment of Zn-Barlowite. The other thing I will say is, like I said, impurity-mediated Kagame layer to Kagame layer coupling is a concern. I can fit it. It improves our fits to our HOL data by around 3%. It's fitted to be pretty weak relative to our other coupling terms. So it's probably there in some extent, but I hope that it's minimal, and I hope that it messes with the intrinsic quantum spin liquid behavior minimally, such that the state is still intrinsically a quantum spin liquid with some impurities going on every now and then, rather than just something that's not fundamentally close to a 2D quantum spin liquid. So with this, I hope I've at least landed several punches in the directions of convincing some physicists here that this material is indeed a quantum spin liquid. So I will come in with the steel chair, hopefully deliver one final blow to leave you all to go home with. And that is, we have a very well predicted magnetic field evolution of what impurities should do in an applied field. Due to the additional Zeeman energy, the impurities lift in a highly predictable way up to slightly higher energies. You can see we're coming in here with an incident energy of 14 Tesla, and this all but extinguishes our low energy scattering. So this is highly suggestive that impurities are being lifted. If we look instead at the same specific momentum cuts I used to show you the presence of a possible gap earlier, we can see how kind of beautifully this low energy scattering is lifted. And we can see that our damped harmonic oscillator fit now peaks around 1.5, 1.6 millielectron volts, which is great because the characteristic Zeeman energy of a 14 Tesla applied magnetic field interacting with 1 Bohr magneton is indeed about 1.5 millielectron volts. It's far from trivial though, because another question you might ask is, wait, isn't the intrinsic quantum spin liquid state gap around 1 millielectron volt, and therefore couldn't an applied field around 1 millielectron volt end up closing this gap and allowing for, kind of maybe the impurity spins, depopulate from low energy, but we get some Kagame modes populating into low energies due to the applied field. The reason this is not the case is although the gap is 1 millielectron volt, that gap is set by the antiferromagnetic exchange in plane, which is estimated to be around 14 millielectron volts for the Zn-Barlowite system. So it's possible with 14 Tesla that we do get a little bit of intrinsic gap closing of the quantum spin liquid state that might fill in kind of this low energy scattering a little bit, but that, I think at least in the modelings I did in my thesis that I probably need to get more detailed about, that the intrinsic gap energy would probably only be closed by maybe even larger magnetic fields. So with this, here are the conclusions of the main part of my thesis, which is, I think, a very exciting advance for the field of condensed matter physics and kind of understanding these exotic magnetic states. We find universal Kagame lattice spin-on-like excitations that are nearly identical between Herbert-Smithite and Zn-Barlowite. And I think this strongly strengthens the gapped Z2 quantum spin liquid claims for those of these materials. So with that, thank you all for attending. It was my honor and pleasure to present my physics defense, PhD defense today to you all. These last 6 years have been very tough for me, but I think in persevering through this, I came up with some magical data. So now for this part of the session, I believe you all will leave the room soon, but if you are interested, I'm doing postdoctoral research on Zn-Barlowite and Herbert Smithite well, and I would be very excited if any of you would be interested in coming back to it. I will say it's not a traditional physics talk, but to entice some of you to come, there will be coups involved, mummies, psychedelics, and some bad behavior on behalf of Stanford. So hopefully that's a good enough hook to get some of you back in the room when we're done with the defense here. But other than that, thank you all for coming.
I think we do have time for a question or two from the audience. If anyone would like to ask a question before we break, please.
Hi, Aaron. Nice talk.
Thank you, Elijah.
Maybe I should know this, given that I spent a quarter in Young's lab. But you have very nice data, and your explanation for why these Kagame lattices don't find the antiferromagnetic ground state is convincing. But what keeps them from finding the ferromagnetic ground state, especially as you go to 0 temperature?
What ferromagnetic ground state?
You imagine on a triangular lattice, all the spins could align, and they'd be happy with that.
Yeah, so I'm going to do a sneak preview of my next slide since you asked a good question. So this does actually happen in real materials. So one material that I hope to study in my postdoctoral research is not Hadeite, it's actually Tondite, which is a Herbert Smithite analog with magnesium on the interlayer as opposed to zinc. So magnesium is chemically, 2+, just like zinc, so it's chemically identical, but it's a much smaller ion. This causes the Kagame layers to space much closer to each other, and indeed, Tondite, which is found naturally in the Atacama Desert in Chile, does in fact ferromagnetically order at around 4 Kelvin. So it's incredibly frustrated. So my best shot at answering your question is that, like I said, and like I fit, I think just the intrinsic ferromagnetic coupling between Kagame layers is there, but I think with zinc in the impurity slot, it's just weak enough to not kind of override this quantum spin liquid state and lead to ordering. But it's an interesting question because in an incredibly related Kagame lattice spin 1/2 space material, we do see this kind of ordering. So yeah, the exchange is there and it's possible. And I hope to measure the ferromagnetic state in Tondite very soon.
Great. Any other questions from the group before we?
One up front.
Oh, please. I'm so sorry.
I know that Young said this during your introduction. You guys feel like you're almost close to definitively saying that it's a quantum spin liquid?
This is a disagreement between me and Young. I'm sold on it. I think Young.
Personally, I believe it. The community needs to speak at some point unanimously, and I don't think we're there.
I guess my question is, what would it take for the community then to say it definitively?
You're part of the community, I assume. I think Aaron did mention that the impurity question, how do impurities affect what we're observing? And I think we're showing more and more that you can distinguish between impurity effects and intrinsic Kagame effects. And the intrinsic Kagame effects are what we hope what is expected in a QSL.
That's a great answer. I'll add something to this. It's maybe a theme in the third part of my talk as well. There's always a difference between what exists in reality and what we believe exists. So I can't answer the collection of, collective construal better than the talk that I gave here. What I will say is I feel like as we get more evidence that more and more people will hop on board, maybe it will take us growing 100% pure zinc barlowite, and then there'll just be a gap and there'll be no low energy scattering and no impurities. I think that would convince everyone, but that might be a ways away. So we'll see where we get in the meantime. But I think studying these related materials and seeing trends in magnetism, again, to pitch this third part of my talk, might also go a long way in kind of showing this thing entering a quantum spin liquid from non-quantum spin liquid states as well.
Great. Is there any last question? Do I see a hand, a question, please?
Last one.
Okay,
Where do the impurities come from, and why were they very difficult or impossible to get away from in your crystal growing?
Yeah, that's a really good question. I'm gonna go back to, there's a slide with impurities on it. I'm back. Yeah, so the reason impurities form is more or less due to thermodynamics. So copper is almost chemically identical to zinc. They're both, they're literally next to each other on the periodic table. Both transition metals, both tend to oxidize two of their electrons. So they're nearly chemically identical, meaning that it's just, from a thermal statistics part of growth dynamics, it's kind of impossible to prevent some of the copper from getting on this interlayer site. And obviously you need a lot of copper in the growth because you need all the on-layer sites to be populated with copper. Thankfully, due to the details of the system, it's actually seems very unfavorable for zinc to end up substituting on the Kagame layer itself. This was an early question that Young had to fight earlier in the days of the quantum spin liquid that I think the field is more or less in agreement on, that we've exercised this ghost, but yeah, it's just kind of something that's chemically unavoidable. So we can, try our best with growths. This is actually another reason I'm interested in studying natural crystals, because they grow through different synthesis pathways. And they grow over much, much longer time periods. We kind of expect, because it's nature, that most of these natural crystals are more impure, but I want to try looking at a lot of different sites to see if maybe a 1,000-year-old crystal might grow under different thermodynamic conditions and maybe help this problem out as well.
Could it be said that the impurity itself is needed as a part of the process to grow the crystals? Or if you could just remove the impurity altogether, can you still grow the crystals?
Yeah, better because the crystals form because we mix like a bunch of powders together, right, that have coppers in it, and then like they'll form to this, and zinc has a slight energetic preference to occupy this site, but the energetic preference is small enough where if you're to do thermodynamic calculations, the copper ions have to be there, and some of them will just end up populating.
So you can't just get rid of the copper because you need the copper.
Yeah, because the copper has to be there so it can be in our Kagame lattice, right? That's the fundamental problem, is you want to grow a 2D isolated Kagame magnetic lattice, but you need the magnetic moments to be present there, which unfortunately means they can sneak onto the interlayer sites.
Anything else, please?
Sorry, do you have a projected timeline or a targeted timeline to convincing the community?
No.
Been estimated?
That's up to the communities.
It's not up to me, it's up to some higher power.
Okay, on that future looking note, I think we should stop this part of the session and congratulate Aaron for their presentation. Who's not a committee member, or Aaron needs to do other things right now, if you would, but there is an invitation, I guess, to come back for that extra part. We don't know how long we're going to be in the discussion, which makes it a little difficult, but maybe Aaron, you'd signal to people or
Send out an email,
an email.
smoke flare.
Okay. Thank you all so much for coming.
I'd hope around 4, usually this takes about an hour.
Our best guess would be an hour.
Okay.
Vatican, white smoke, black smoke.
And Jeff, if you can hear me, we're gonna start a new Zoom session for the private part. Do you think he's hearing me? Oh, is he there? Oh, okay.
Yeah.
Oh, good. I think he's. All right, so,
Thanks, Jeff.
yep, we're gonna exit this Zoom session and start the new Zoom session. Both of us can host that. I can
Do you
start.
mind doing that?
Yep, I'll do that. All right. And then
If we need to take a couple minute break, bathroom bio break, why don't we do that for, take a few minutes and then we'll reconvene.
Zoom's still there.
He'll have to log out and log back in, so hopefully,
But
yeah, I
let's
think
assume that
it's on right now, so we should.
still.
Tried growing the magnesium analog?
Not as crystals, as powders. We did that back at MIT, yeah. For some reason, magnesium, there's like a limit around 75%. Trying to make that, as close to 100% as possible. Just couldn't push it Yes, I'm about to start the new Zoom session.
Yes, thank you for checking on
Thank
this.
you.
Let me look at the magic ingredients in here. So do you want hard copy or you said
I am
digital copy, right?
amenable to anything. If you want to do a digital copy, that's perfectly fine to me too. It's less printing for me, but that's just standard.
Okay, great.
case. There's also like a.
So you don't mind, we don't need individual signature, or we do need
It's just your signature.
my signature and you don't mind digital?
I do not mind at all.
Okay, great, good.
Cool. Let me know
Thank you so
anything
much
else.
for popping in. Sounds good.
Thank you.
So Jeff, if you can hear me, I did start the new Zoom session, so you might want to pop into that.
And how would you like to configure? Do you want Aaron, I mean, does this work just like that?
This would still
Aaron
work.
can- Yeah.
You can choose to ask questions.
Yes, great, good.
Aaron, can I ask you to hop on to our new Zoom session? Do you have
Is there a link for this?
Let me forward that to you.
Should end the session.
Yes, and end the
Thank you.
current session.